just going to pick it up where Kiriti left off on automation, and me and Andy are going to talk about a real project that actually started a little bit over a year ago with an RFP received from an ISP, from a carrier, and we really didn't have a product yet that fulfilled that RFP. But in a little bit over a year, thanks to automation and thanks to big help of open source, we managed not only to basically build a prototype, but also have that prototype beat the competition and being deployed in a real network. So first, it's about the carrier project that talks about lightweight 4/6, and I will give a quick introduction what that really means, what that brings to a carrier. Then we go into this open source project and why it's actually cool and why we needed it, and that's what Andy then takes over. And then I explain the different steps, high level, that we took from a prototype to real product. And the most important piece of the talk really is that we didn't change a single line of code in Junos itself. We just leveraged what's there. So everything we're going to show here is running with 16.1, and the project didn't exist before 16.1 got released. So the release got out, and the product came later. And if you have time this week, see us in the booth, and we can show you how that actually looks like. So lightweight 4/6 is really about the transition problem that carrier have for residential subscribers, how to bring them away from IPv4. Basically, the v4 address space, as you know, the public is really a scarce resource, and you want to limit the use of that. Now, the classic way is just give everybody v6 and v4 and hope that at some point you can turn off v4. Well, that didn't really turn out to work that great. So the next best thing is to do address translation at the edge of the network, and that's what DS Lite is offering you, which is great for us vendors because we can build this really complex carrier-grade NAT device that you will have to deploy, which is completely stateful. We can offer you with redundancy and such. And the client is basically just tunneling everything over IPv6. And he gets to use just a private IP, so he doesn't even know anymore his public IP, and that's it. Now, lightweight 4/6 is an RFC that is out there for some time, and it flips the complexity of the dynamic address translation back to the client. I mean, after all, every CPE already does address translation and port-based NATing. That's an intrinsic function he has to do anyway between the LAN interface and the public IP address it's given. But the difference in lightweight after and this solution is that clients share the public IP address, and every client gets the same IP address, or at least a whole bunch of clients, but they only get the limited port range to use out of that vast port range that you have for an address. So that makes the edge function stateless, because you can simply have a static mapping. And to show you how this mapping can kind of look like, I have another drawing where I show you a very simple binding table where you see the IPv6 address that are assigned to every CPE out there. Those are just public IPv6 addresses, all unique, nothing special. But for v4, the v4 client, which is the CPE, is given, or some multiple of those are given the same public IPv4 address. But the port range they can use for address translation is limited. So you see, with that, if you have that mapping table at the edge, you can do the encap decapsulation of the packets, and the dynamic port mapping is done by the client. Now, Linux and OpenWRT can do that already. That's just an option you give to iptable. So that part was quite easy. The harder part is how you deal with that binding table at the edge. And why is this an interesting solution, lightweight after? It's really because it's completely stateless. So here we show like 4 instances of this VNF doing those lightweight after function, and they all share the same binding table because there's no state problem. And then the data center upstream and downstream router for v6 and v4, they just learn the prefix for the public IPv4 address through any of those instances, and they just load balance the packets. And even for the same flow, it doesn't really matter. For the single flow, you can just spread the packets around. And if one instance dies, well, sometimes software fails. So if that fails, then it's quickly picked up as not an eligible next hop because the routing updates don't get through. Hence, the traffic just gets distributed to the other one. For me, that was one of the first real scale-out solution that really works because the config is equal on every of those instances. Now, I said we started with an RFP that we got on the table, and that was kind of part of the, you know how RFPs are, they have 100 times more of those topics on it. But basically, the ask was to support millions of stateless tunnels, do the port range mapping, do that at IMX line rate on every 10 gig port, even though it's a VNF, a little bit of challenging, and just to make it a little bit harder, also do fragmentation and reassembly, because it can happen, thanks to the encapsulation, that you get these kind of nasty packets. And support dynamic resiliency and such. Now, we did look at the vMX, that's what we started with, that's what we have. And we managed to use tunneling cap function via filters, and we got a blazingly scaling of 4,000 tunnels per vMX. Now, when we tried to fill out the RFP with that scaling limit, the only person that was happy was the salesperson, because the numbers turned out really big, but of course it was by no means competitive. So the next best thing we did is, well, maybe somebody else solved this problem already. And then we actually got a hint in the RFP itself talking about Snabb as an open source packet engine that is really, really fast in providing sort of NFV capability to virtual machines. So we explored there a little bit more, and to my and anybody else's biggest surprise, there's actually an app in that Snabb open source, which Andy talks about a little bit more, which does actually help, or it offers that translation function as part of that engine. But that engine is limited. It's limited not in the number of tunnels it supports. It scales to ridiculously high numbers. It can do line rate for IMX. It drives 10 gig ports. But it has like a static configuration. So there's no BGP here. I think it even has trouble, not mistaken, or neighbor discovery it can do, but that's about it. So, Andy, if you're okay to talk a bit more about Snabb.
Thank you, Marcel, and thank you, Juniper Tech folks, for having me here. It's been lovely to work with y'all over the last year or so. I work with a company called Igalia, or a small open source consultancy, and we've been working on Snabb for a few years now. So this part of the talk is introducing Snabb. What is it, and what does it provide in this use case? And our tagline is simple and fast packet networking. So I want to go dive into that a bit and see, what does it exactly mean. Snabb is a workbench which you use to develop network functions, specifically the data plane of network functions, right? That's where we focus. And when we talk about simple, we try to make simple software. We don't try to complexify things too much, and simplicity is a virtue. In the early days of Snabb, we actually had a code budget of 10,000 lines, and that the thing should build within a minute and produce an executable that was a megabyte or less. As we've expanded and added more programs horizontally, we've torn down those walls around our city, but they were very useful in helping us design solutions that had a simple structure so that we could quickly prototype and try out different data planes. So one of the examples of the simplicity is that it's a kind of boxes and wires sort of model. It's a toolkit. There are some included network functions, but it's definitely designed for people to prototype and build new things. So here would be an example. We have, we're reading packets off the receive buffer on a NIC on the left, passing it through some kind of filter. We have a compiler actually for the TCP dump language that does quite high performance filtering, and then passing it again to a NIC, right? We have a bunch of apps in there, like Marcel mentioned. We have the fragmentation, reassembly, and fragmentation. Our ARP stuff works now, but it wasn't before. So that should give you a flavor of the age of the process, of the project. It's kind of young. So when you want to add, for example, fragmentation, like reassembly and fragmentation around a simple app like this, you simply add a couple more apps in the pipeline, so to speak. You add your reassembly app, for which we have for v4 and v6, and you add your fragmentation app before pushing packets out the other side, and it just works. It's a very simple change. It's literally a couple of lines of code that you add to your network function. And when we say, okay, so simple, fast, packet networking. So we've done simple, and now we're on fast. And how is it that we actually get speed? I made a drawing here. It's probably not intelligible at all. It has two colors, right? It has a gray color and it has a green color. And the gray color indicates the kernel space, which usually in a Linux system is what manages a network device. But it's too slow, as most of you know. The kernel networking stack just can't really handle a lot of small packets, for example, or ad hoc functions that you want to prototype. You have to put code in the kernel. It's quite irritating. So what we do is we do everything in user space. We actually bring up the card in user space. We map its registers in user space. We read the packets off the ring buffer in user space. And we have the NIC depositing its incoming packets directly into the cache on the CPU, effectively. And then once we have it there, we can perform really high-touch operations on the packets. We don't have to worry about, since we've taken that hit of copying it into cache, it's not really expensive to access different parts of the packet. So you can build new and interesting networking functions without asking yourself, what offload features does my NIC support, for example? So right, packet networking on the other side. Snabb is a data plane project. It's a project which you use to tie together boxes to make data planes. And here is Snabb in an entire slide. I know it's words and not pictures, but it's really quite simple. A Snabb app is a series of breaths, and a breath begins with inhalation, and then it continues with processing. And inhalation pulls some set of packets into the system, usually from receive queues on NICs. And once all of the sort of inhalation parts of your pipeline have been visited, then each app in the pipeline is called to process its packets on its input queue and push on its output queue. And that's it, right? That's the whole thing. So it's something you can get in your head, and when you have your idea about what kind of networking function you want to build or integrate, as in the case of Marcel, you can just build it. So it's excellent for building prototypes. It's excellent for taking prototypes to production, as Marcel is able to do. Some examples. So I know many of y'all test out things in networking. So these slides are available to you afterwards. But if you just git clone the project, CD into it, and make, you'll have a binary within a minute, right? That's there for you to run. So I definitely recommend all of you to give it a try sometime. So, and if you just run it, they'll say, which program do you want to run? And we have a few of them, and I'm going to mention 4. The lightweight after, the packet blaster, which is really useful for load testing your network functions, the NFV, which provides the host level it's a virtual switch, and Snabb vMX, which Marcel built. So the lightweight after is the function that we built for a carrier, which Marcel was able to take advantage of. All of this is open source, by the way, and it can manage a binding table of millions of entries. And its performance these days, if you configure it in an honest stick way, in which it manages just one NIC, you can get about 4 million packets a second, which is not 64 byte, but it's still pretty good, and it's line rate for IMEX at least. And that is the unique feature, that we have this binding table that can scale to millions and millions, and millions of entries, actually. And Marcel will give a bit more details on that. After that, this is the one I think actually is the most likely to be useful to y'all. It takes a PCAP capture of packets and blasts them out over the card. It'll actually put them all in the transmit descriptors on the card. So you can run many of these, and it can saturate links and 64-byte packets, see the return traffic, and count like how many packets you're missing. It's great for testing like some third-party device in a very low overhead way. And it's also possible to synthetically generate the packets which you send over using Lua, which is a lightweight scripting language. Snabb is written entirely in Lua. The NFV provides networking to containers, and it can do the 64 bytes per packet on a full duplex 10 gigabit link, and we're working on scaling that to 100 gigabit somehow. This is with one core. The 100 gigabit scaling will involve multiple cores. And it was the first major Snabb networking function that was built. And then finally, Snabb is a data plane, right? So it's great at pushing packets along, but it's not a netconf endpoint, and it doesn't implement BGP. So those are two things that you definitely want when integrating a network function in your network. And that's what Marcel built, wrapping the vMX, joining the data plane and the vMX features. Maybe this is a good time to hand off then to get back. Give you this.
now we know that we have a vMX. We didn't scale alone, and we have this open source project which really scaled dramatically well. So how can we build something together? And this is really, I put it down into 5 little steps, how we took it from having nothing to having a real solution. The step 1 is really using Snabb. What Snabb does, it provides connectivity between a 10 gig port and the vMX. So here around the vMX on top of QEMU, and I just use Snabb to offer virtual I/O connectivity. Interesting enough, if you do this in your lab, you can actually beat our data sheet who says you can only do 3 gigabits per second in VirtIO on vMX easily by double or more. You can even nearly fill actually a pipe with that, because the packets are actually handed over using vhost user, which means there's 0 packet copy between the NIC and the packet arriving in the vMX. So here, the vMX is just talking to the data center router connected, nothing special. The second step is to basically turn on the lightweight after function. Think of it as a bump in the wire. So adding some logic into Snabb that tells them, oh, this is a lightweight after packet. I have to do some tunnel encap decap. It's similar as to those traffic shapers that you have, you can put into a wire. And this logic was quite easy to build into Snabb because it has those chaining function. I just needed to write a little application that detects the type of packet it is, and okay, I just pass it to the vMX, or I have to do some encap decap. And that means with that and some static configuration, we already managed to kind of build the solution that at least scales up and performs quite well, because the heavy lifting is done by Snabb itself, and the vMX is just there to do the control plane traffic and the routing when the packet hits the vMX after it's encapped or decapped. So the third step was then to knowing that usually you only have 1 or 2 upstream routers that you talk to. So you still want to do BGP and all that stuff, but the next hop is hardly going to change. So we added some cache refresh function that instead of sending every packet to the vMX just to be routed back, we just send a test packet every second to see if the next hop has changed or not, and cache that and use that. So that means all data traffic is actually passed only in the Snabb layer itself instead of the vMX. Then we needed some control function to drive the Snabb layer, and we wanted to hide that all behind the vMX, and that's where the automation really comes in. Thanks to custom YANG, that we can add any kind of YANG module schema into Junos at runtime. We added the ITF YANG model for Softwire, tweaked it a bit, augmented, etc., what we needed, and with that we can configure the lightweight after function in Snabb completely through netconf YANG through the vMX. I think that was really cool, having a 16.1 release and just adding, learning him a few more tricks. And it doesn't stop by the configuration. It actually, we added SNMP MIP support, and we added show commands and monitor commands as well, all done at runtime. So here, with that, we already had a solution that we were able to actually go into a POC with. But it was still kind of clutchy because you had to tell, okay, you have to install KVM, you have to install vMX on it, or Snabb, and you have to configure this application that talks to each other. It's not a complete solution. So that's where we added Docker as a mechanism to package everything neatly together. And by building a Docker container that has all those components in it, the open source elements in it, and just adding the vMX tar file at runtime made it possible to be really independent of any platform it runs on. And this is all this part is all open source. So we went through the outbound approvals and everything to publish that, and we had the work done on the prototyping thing. We needed then the help of Andy and his colleagues to basically productize this and also upstream all the changes we did into Snabb into the project itself. So a commercially running container looks then like this. We have the container where you have KVM in it and the vMX with the control plane and the forwarding plane. And here we actually run 4 different Snabb instances, each driving a 10 gig port, each having a binding table of multi-million entries, each providing line rate at IMX. And when you talk to a carrier about line rate, they're not looking at the performance number. They're looking at the number of packets you lose while doing that. So we actually had to pull the numbers of packet loss, and that has to be near zero. So again, the control traffic is done transparent. So the upstream data center router, he talks to vMX. It's no different. But the user traffic is basically handled at the driver level, at the Snabb level directly. And this really has become a solution that offers a high performance solution to this RFP. Now from, I said, a little bit over a year from the RFP, not only won the RFP, but it also, I heard that last Friday, the first production customer is actually running over this solution. So in summary, it's really cool to work and leverage what's out there on the open source. And at least with the Snabb community I was introduced to, it's really a pleasure to work as long as you also contribute something back. So it's kind of by both ways, but it worked really great. And Junos, with the capability of enhancing the control plane with custom Yang or ITF Yang models, really makes it a perfect solution, not just for this lightweight 4/6 project, but probably for other projects as well that you might have. Happy to talk to about that as well. Thanks very much.